Weak stationarity requires a constant mean and an autocovariance that depends only on the distance between two periods, not on the calendar date. Setting the lag to 0 gives constant variance. Intuitively, the series should have the same probabilistic appearance wherever we inspect it. Output in levels typically violates this condition because of its upward trend. Log-differenced output, which resembles a growth rate, is a more plausible stationary series. Stationarity is not a technical decoration. Under stationarity and sufficiently weak dependence, time averages converge to population means, least squares estimators can be consistent, and central limit arguments justify inference. With non-stationary variables, a regression may be spurious, test statistics may not follow their usual distributions, and apparently significant relationships can be meaningless. The practical rule is simple. Inspect and test the series, then transform non-stationary variables before fitting conventional dynamic models. The autocorrelation function measures correlation between the series and its own lagged values. The sample version compares deviations from the time average at two dates separated by a chosen lag. A stationary short memory process usually has autocorrelations that decay quickly towards 0. A non-stationary series often decays very slowly. The full sequence across lags is more informative than one coefficient because its shape reveals persistence, seasonality, and clues about a suitable dynamic model. Swedish output in levels has a slowly decaying autocorrelation, still substantial after many quarters, which points to non-stationarity. The sawtooth pattern at multiples of 4 signals quarterly seasonality. After taking log differences, the autocorrelation falls quickly and is near 0 beyond the seasonal lag, making stationarity more plausible. Use the autocorrelation plot both as a diagnostic and as a guide to which lags might matter in a subsequent autoregressive model. A first difference subtracts the previous value and removes many stochastic trends. For an economic series that grows proportionally, the log difference is more natural because it approximates the percentage growth rate. After differencing, return to the autocorrelation function. The transformed series should lose the slow decay of the level. Differencing is not automatic improvement, it changes the estimand, so interpret the resulting model as one for changes or growth rather than for the original level. A deterministic trend follows a fixed function of time plus a stationary disturbance, so including time as a regressor can remove it. A stochastic trend evolves through accumulated random shocks. Swedish output growth varies across decades in ways a single linear time trend cannot capture, so differencing is more appropriate. Distinguishing the two matters. Detrending a random walk leaves non-stationarity, while differencing a truly deterministic trend may discard useful long-run information and create unnecessary noise.